What's up, gophers? Is it just me, or is it time for another C++ tutorial? Which, if you don't know, C++ is the very best programming language on earth, way better than Python. The more astute will probably be noticing a significant change to the channel, and that would be my beard. This thing's pretty much a forest already. I have to get a chainsaw to hack it down. But I'm not going to. I'm growing it out. The plan is to grow a handlebar mustache all the way like this and just shave everything else. Here is where we left off in the last epic video. Everything seems to be alright and well in our world, but if we pull up a simple performance monitor, we'll notice something going on here, and that's we're taking 100% of one of our cores of our CPU. That's a big no-no. Our game is only rendering 5 sprites to the screen, so for 5 sprites, using 100% of the CPU, in other words, we're doing a whole lot of nothing and using a whole lot of everything.
Hey Marty, I thought you said C++ was the best and so fast, and why is it taking up all of our CPU usage?
Before we start panicking, jumping ship, and moving back to Python, we've got to understand that our program is doing exactly what we're telling it to. Every single piece of software or game that has some sort of loop has a main loop, and our main loop is right here, while game running. So far, our main loop is very simple, and all it says is, hey, is the game running? If it is, gather some events, clear the window, draw the entities, and display the entities. Computers aren't that smart, and they'll just do what you tell it to, which probably isn't a good idea. If you give a set of instructions to a computer, it will try to execute it as fast as possible. Why would it want to go slow? Again, is this Python? Now here's the problem. We haven't set any limits on how much of our CPU can our program use. One approach to this is simply to limit the amount of times that the game can update per second. While that works to a degree, it's not the optimal solution, because if you said, alright, we'll only update 60 times per second because we're only going to render at 60 times per second, or are we? Let's say we've got a monitor that renders at 144 frames per second. As you see, it's not optimal. What we actually want to do is limit the amount of times that we render to the screen per second and set it to match the amount of times that the actual display renders per second. This is incredibly simple to implement, and if we go into source renderwindow.cbp, all we have to do is add another flag to our renderer creation call right here, line 18, renderer equals SDL create renderer. Throw in 2 ampersands, which is to say and. So in addition to being an accelerated renderer, we are also going to only render as many times per second as the actual screen can handle. So the flag for that is SDL underscore renderer underscore present VSync. So what's called VSync, and VSync essentially just caps your display rate to be whatever your screen's display rate is. Control save that and ensure it compiles and runs all good. Now it's going to give you a little warning that there's an enum and a boolean context, but we don't care about that because it hasn't broken the ship. The ship's still sailing. As long as if there's not a massive cannonball in the deck of the ship, we're good. If we're floating, we're floating. No need to fix that which is not broken. What we want to do is limit the amount of times that our code updates per second, but also simultaneously render to the screen as fast as the actual screen can handle it. So how do we do that if this is all part of the same while loop? Well, we open up another while loop. Let's start off by creating a new file, control N. Start it off with a hashtag pragma once because this will be a header file. Hashtag pragma once. Be sure to include SDL. Hashtag include SDL2. Hit enter, and let's just control save this so we can get some nice syntax highlighting. Control shift save. Save this inside include. Save it as, we're going to call this utils.hpp. Utils stands for utilities, and this is where we're going to store all sorts of utilities, such as nice little printing functions, and in our case right now, a function that returns the elapsed time that the program has been running in seconds. So hit save, and now open up a new namespace. So all you have to do is type namespace. We're going to name this namespace utils. Hit enter. Now what is a namespace? A namespace is essentially just a group for your code. So if you had an integer x inside the namespace, to access that x, you go utils and then : x. All it does is just create categories in your code to help you better organize it. So type float, and we're going to call this function higher time in seconds. It will not take any parameters, and open up some curly braces. Now we can actually mark this function as inline, which essentially just says, hey compiler, we're going to just declare that we're going to have a definition to this function right here in the header file. So all we go is we go float t equals SDL underscore get ticks. We'll which will get the amount of milliseconds that has passed. Now, since this is in milliseconds, we're just going to scale that up to a second. So all we do is go t times equals 0.001f. Last but not least, we return t. Very simple little function. Go into main.cpp, and at the top, be sure to go #include utils.hpp, control save. Alright, so now we have a function to measure the amount of time that has elapsed in our program since the program began. And we can test this out by going into while game running, and it doesn't matter where, as long as if it's not in this for loop here. We'll just go std cout utils higher time in seconds, and then std and l, and we'll just see that it prints out the amount of time since the program has started in the console. And a little slight error happens to the best of us all. Okay, so it's not get tick, it's get ticks. So in utils.hpp, make sure it's get ticks, and then go to main.cpp, hit F7. Hopefully it should work. So we see in our console here, it's saying, all right, 3, 4, 5, 6 seconds. All right, so let's kick this off with a constant float time step. So this number right here is going to be the amount of time that we advance the simulation forward by each frame. To keep it simple, let's just set our time step to be 100 times per second. So set that equal to, well, 1 divided by 100 is just 0.01f. We set it to be constant because we do not want to change the time step once the program starts. Next, we're going to create a float called the accumulator. So what does that do? Well, let's just set it to 0.0f for now, and we'll explain that later. We need one more variable, and that is another float, and this is our current time, and that will be equal to utils higher time in seconds. This line here is the time going forward. This is 0 seconds, 1 second in, 2 seconds in, so on and so forth. Each vertical line represents an update to our game. As we're currently standing, we're telling the computer to update as many times as it can per second, which in turn ends up looking something like this, with just an infinite amount, well, not infinite, but a lot of updates per second, and a lot of them aren't even necessary. You get the same exact picture across, the same smoothness, without a lot of this wasted CPU usage. So it's just overheating, it's making a bacon sizzler out of our CPU for no real reason. A well-behaved application, on the other hand, limits the amount of times it updates per second. So for example, if we had a car in our game that was moving forward by a given velocity, we'd say, okay, we're going to have an accumulator. That'll be some sort of threshold, so essentially a bar of time that needs to fill up. Once the bar gets completely full, we'll reset it back to being empty, and then we'll move forward 1 time step. So now we will be here at this time step. At each time step, we run the main gameplay loop. Car is moving forward by a given velocity, then every time we run the update function, then we'd want to, well, update everything in our game. So we'd want to move forward our car by some velocity. The simulation advances forward, and our car moves forwards by a blip, moves from here to there. As we move forward in time again, the accumulator begins to fill up once again. Once the accumulator gets full and we are at our time step, then we empty the accumulator and we update the game again. So now the car moves forward by another given amount of time, from here to there. In this example, we are updating our simulation 5 times per second, which is actually kind of slow, but I don't really feel like drawing 60 little bars because that's going to take all day. All sounds great, but the one remaining issue with this approach is that, as you'll notice, it doesn't look that appealing to go from here to there. It's a little jittery, you know, it doesn't really look good. But there's something we can do to solve that. For demonstration's sake, let's say our car moves from here all the way over here, in between these two here. So in this time step right here, our car moves from point A to point B. This is actually going to look terrible if we render it just like this. Luckily, we do have a solution that's actually very easy to implement. If we record the previous position of the car, what we can do is we can take a guess of where the car would be in between our updates, in between each time step. So say if it was halfway, then the accumulator, which we mentioned before, would be half full at 50%. Then what we can do is we can actually use a linear interpolation to take a guess of where the car would be in between the updates. So if it was at 50%, we'd render it halfway between point A and point B. If it was at, if the accumulator was 90% there to the next time step, we would render it 90% of the way to the next time step. This way we get a very nice smoothed out movement. Now in order for this nice smoothing out to happen, we need the renderer to be running as fast as it can within one limitation. And that is, of course, there's no point in rendering faster than the display can actually handle. That just makes no sense at all. So then if we were updating our simulation 5 times per second, we could actually render this all at as high as we wanted. We could render this at 60 frames per second and it would still look good. It would look smooth. You wouldn't even be able to notice it. The only thing you would be able to notice is that the controls would be a little rough. The controls would be rough, and if you had any sort of physics rendering at only 5 updates per second, it's going to be highly inaccurate. So the higher amount of updates per second to the physics of the game, the higher the accuracy of the physics. As nice as infinite accuracy would be, we don't have infinite computing power. Our game is going to be a 2D platformer, and we're not going to need any high degrees of accuracy. We just want it to be believable to the player, that it's convincing. So we could actually just update at 60 times per second. Now I actually like to update at 100 times per second, and the only reason for that is it's a nice number to work with. That's the only reason. I would go with 60, but 1 divided by 60 is like 13.337 or something. It's long, not that easy to remember. I prefer just 0.1. If you have any questions on the concept of a proper game loop, I'll leave a link in the description to Glenn Fiddler's Fix Your Time Step article, which was very, very useful and helped me out a ton. So now that time step, that's the amount of times per second that we will step forward in our simulation. The accumulator, well, that's that bar that you saw previously. The accumulator needs to equal a time step in order to take a step forward in the physics. Alright, so go into the while game running loop, and the first thing we're going to do is create a float and call this new time, and set that equal to utils higher time in seconds. So that is the new time. Then create another float and call it float frame time. The frame time is the amount of time it took for a frame to complete. So frame time equals our current time minus our new time. Actually, that's reversed. It's our new time minus our current time, because our new time is going to be fresher, therefore it is going to be longer. Once we compute our frame time, we can set our current time to be our new time. So current time equals new time. And now we want to add to our accumulator. We want to accumulate some time. So accumulator plus equals our frame time. Hit enter and open up a while loop. So while our accumulator is greater than or equal to our time step, or you can call it your delta time. I just call it a time step. So what this means is if the accumulator has exceeded the threshold required to update our game, well, then we shall update. So you can just move all of this while SDL poll event, just Control X that, and then paste that right here. So if we have accumulated enough time to take a step forward in our simulation, then we want to subtract from our accumulator minus equals the time step. So take away a time step from the accumulator, as that time step has been now processed. There's no longer any need to store it in the accumulator. So now, depending on how fast your computer is going, you'll probably end up with a little bit of time left over in the accumulator. Outside of the while accumulator loop, we are going to want to create a new value, and it's going to be a constant float, and we're going to call this alpha. So alpha is simply the time left in the accumulator as a percentage. To linearly interpolate between two states, we need to give it 2 states and then the percentage of how much is state B from A, or vice versa. Getting that percentage is pretty simple. We just go alpha equals our accumulator divided by our time step. What percentage of the time step is our accumulator currently at? Is it at 50%? So scroll down and take out the std.cout of where we print our hired time in seconds. No need to print that. This is actually Marty from the day after I recorded this. I did not realize it at the time, but to use the SDL_renderer present VSync actually causes massive issues in the program. So go into renderWindow.cpp. I have no idea why, but for some reason when VSync is enabled and then you rotate anything and then you zoom in on that really far, it just distorts. It distorts everything even if it's not rotated, and it also just makes it run really terribly. So we can't use SDL's VSync. So go into include, open up renderWindow.hpp. We're going to add a new function, and it's going, or a new method, and it will return an integer. So int, and we're going to call it get refresh rate. It will take no parameters. Control save that. Go into renderWindow.cpp, scroll down, and typically I like to have my source file match up with my header file. So that's right after load the texture. All right, then we have ourselves int render window, which is to say that this is part of the render window class. Render window colon and get refresh rate. We're going to do a hacky version of VSync and essentially not allow our program to render faster than our display rate without using the actual VSync. All right, open up some little parameters here. Create a new integer, display index, and we're going to set that equal to SDL_get window display index. So what's all this nonsense about? Well, okay, this is a very simple little function that takes in our window as a parameter, takes in our SDL window as a parameter, and all it does is figure out which window is or which screen is our window on. In the event that they have multiple screens, we want to figure out which screen is our window actually rendering on. Hit enter and then create a SDL_display mode, which is just a nice little struct filled with wonderful goodies packed inside it, such as our display rate. We'll call that mode, hit enter, and now go SDL_get display mode and open up some parameters, and inside there we're going to pass in our display index. So which screen, because you know different screens have different display rates, so we want to go with the screen that we're rendering to. So our display index 0, this is going to be our mode index. So a 60 Hertz display can also render at 30 Hertz. They have different modes, so we're just going to go with the 0, which will give us the highest mode, and then pass in the memory address of our mode. Add a semicolon, hit enter, and now we just simply return mode.refresh_rate. End that line with a semicolon, go into main.cpp, and right after we create our window, we can go int max or let's just call it window refresh rate equals window.get refresh rate. Bingo. The little pop-up to buy Sublime Text is actually part of the experience. You don't get the full unlocked version of C++ unless you don't buy Sublime Text. To test this out, let's go std:/cout our window refresh rate. Why are we even having a variable if we're just typing out window refresh rate? Yeah, we're just gonna take it. We don't need that variable actually. We can just take it out like so, and then std:/L, control save, hit F7. See what happens. Go into renderWindow.cpp. Slight little error. Okay, it's not a method. No. Refresh rate is simply just a member of that struct. So go to main.cpp, control save, hit F7, and it should print out 60 to the console. 60, yes, because my monitor is at 60 frames per second. All right, so copy that, control C, just to keep it handy, and then take out that C out, and we shall scroll down to the end of our function. So what we want to do is we want to perform a test to say, okay, we are going to have a minimum amount of time that we want a frame to take. There's no reason to go faster, as it would just warm up our CPU and the viewer wouldn't even get the pleasure of viewing that. I mean, they could warm their hands beside it and unthaw their toes, but that's about it. Maybe sizzle up some bacon and eggs. All right, so basically the check is, okay, if our game is running too fast, well, game.slow down. Very simple and easy to understand. Or not game.slowdown, but just game.rest. And that comes in the form of SDL_delay. delay. So how long do we want to delay for? This takes in an integer as milliseconds. So 1000 milliseconds would be 1 second. Scroll up to the top of our while game running loop, and we're going to create a new integer here, int start ticks. So start ticks will equal SDL underscore get ticks, and make sure you end that with a semicolon, because semicolons are wonderful things that every programming language needs. Scroll down, and now what we want to do, go int frame ticks and set that equal to SDL underscore get ticks minus start ticks. Tick, it should be ticks. So start ticks. Yes, make sure that's start ticks. Very important to be plural. Now we can actually modify the if statement to say if our frame ticks, so the amount of milliseconds it took to complete this frame, is less than the minimum amount of milliseconds required for a frame to complete, then we're going to go to sleep for the difference between the two numbers. So minimum minus our frame ticks. Our minimum is simply our window dot get refresh rate. This will return the frames per second. Now we want to know the amount of milliseconds per frame. So to do that, we simply divide 1000 by our window.getRefreshRate. Control C that and replace that minimum down below like so. Make sure you end that with a semicolon. Very, very important. And now if you go control save, hit F7, it should all work. And what's the nice thing about this all is if we open up a system monitor, we will find we have an initial spike here, right? An initial spike to get the program going, but then after that, it's actually reasonable. This is actually, you see, okay, this is pre-program, now the program starts, and now you can't really tell a difference. If we go into processes and we scroll down and we look for our game, what do we call it? We called it game main right here. This is it. You'll notice it's not even using a percentage. It's not even using a full percentage of our CPU. Actually, it's OBS that is hogging up the goodness, and a simple screen recorder. So yeah, our game is now only taking not even a percent of our CPU. So this is all working exactly how we want it. The lesson to be learned here for today is don't use SDL VSync. I don't know why, but it's just completely garbage and it's just messing up. It's broken. VSync with SDL is just a big no-no. Instead, we want to use G-Sync, which stands for Gopher Sync, which is the little system that we just set up right then and there. Thanks for watching and subscribing. Make sure you code like gophers, and I will see you in the next video, but not before a quick word from our sponsor, McVanBuck. McVanBuck is a hilarious humor book written by my dad, Peter in Mast. Funniest book of the year, according to myself. If you want to support the channel, buy the book on Amazon. A link will be in the description below, and let me know either on Discord or here on YouTube that you bought it, and I will receive a small commission. A little percentage. Laughter is guaranteed.